So now let's go ahead and get some practice with drawing some actual Newman structures. To make this a little bit quicker, and so you don't have to see me draw the same thing, I actually have some that are already kind of pre-drawn. And looking at these just by themselves, we can already start to classify them as one of the two main, big categories for our types of conformations. And remember, these are going to be our staggered and our eclipsed. So when we are completely spread out, like we see in these bottom three, that is our staggered conformation, which are going to be all of these. And then our eclipsed are going to be the ones when they're on top of each other. And what we're going to do is we're going to choose a random molecule, and we're going to go ahead and fill out all the locations of the possible substituents meaning the other stuff, our hydrogens, our other carbons, bromine, chlorine, fluorine, any other atom that's going to be attached to our main thing of interest, which is going to be our 2-carbon backbone that we're going to be thinking about. So let's go ahead and maybe think about the molecule of butane. So from naming, but we know means 4, and ane means it's going to be fully saturated, meaning all just single bonds. So that is going to be a system which we draw our skeletal just like this, where we do just a total of 4 points or 3 lines that are going to show the 4 carbons which are bonded in our butane system. And in this case, we're going to specifically look along our carbon 2, carbon 3 axis. So in terms of our locants, we could do like 1, 2, 3, and 4. And we are specifically going to be looking along this 3 and 4. You can look at any axis. You can look along 1 and 2, but that's going to be kind of a little bit more boring. So we're going to look at 2 and 3 here just to see all of our different interactions, including our gauche and our anti. So in a conformation, we're going to have our eyeball, and the 3 lines there are my eyelashes. And we're going to be looking along this carbon 2, carbon 3 bond, and we're going to be drawing all of the different possibilities for our rotations as we rotate that 2 and 3 bond to all the different sides. It is helpful to maybe get an idea of what all the different groups are. So here, let's go ahead and just draw, maybe this is going to be carbon 2, and then our bond, and carbon 3. And then think about all the things that are attached to it. So on carbon 2, we know we're going to have carbon 1, and we're also going to have carbon 4. All of the other things are going to be our hydrogens, and we're going to have a hydrogen that's going to be coming out towards us, which we can depict with a wedge on each of those, and then a hydrogen, going away from us in each of those, which we can depict with a dash. And in this case, our eyeball is going to be looking directly along this plane. Now, before we start drawing, let's go ahead and just go back to our model here. So we have 2 carbons. Maybe let's do it. I think this is a little bit closer to what I had. So carbon 1, carbon 2, carbon 3, carbon 4. Maybe do I have it like that? Yeah, I think I have it like that. Where we have all of our different carbons along. Now, when we're looking at our Newman projection, what we're going to do is instead of looking at this in a zigzag, we're going to rotate this where our 2 carbons, our carbon 2 and carbon 3, are going to be directly on top of each other. And we're going to be looking at all of the different conformations as we rotate these around. And each of these are going to have specific names associated with it. So any of the ones that are going to be spread out, where you have all 6 groups easily visible, are going to be our staggered. And then any of the ones where you kind of have like the 3 in the back, which are kind of hiding because they're in a eclipse structure. So if we think of all of our different conformations, this very first one, where my 2 carbons, my CH3s, which are going to be much bigger than my hydrogens, so we just have here a red ball. In reality, there'd be 3 more hydrogens off those, but we're just going to make it a little bit simpler here. When my 2 big groups are the farthest part as possible, this is anti. So I start with an anti-conformation, for example. I take and I rotate one of them, in this case, our front carbon, by 60 degrees, and we're now in eclipsed form. If I go and I continue to rotate, This is going to be in a gauche because my two big groups are going to be 60 degrees apart, but still staggered. So this is staggered and gauche. I can then continue to rotate, and this is going to be anti again. Now this anti is actually going to be a little bit more expensive in terms of our energy because I have really, really big sterics for my two big groups. If you remember, if I unrotate this back to here, in this case, I still have an anti, but I have a big group and a little group, a big group and a little group, and then two little groups. Where if I go to this conformation, I have two big groups, which is going to be really, really expensive in terms of my energetic costs. I can keep rotating, and I'll go to another gauche, another eclipsed, which is going to have same energy as that first eclipse, but lower than my second, and then back to my anti. And those are going to be all the different conformations that we're going to go through. So we'll have anti, eclipsed, gauche, eclipsed, gauche, eclipsed, anti. And that's our full 360-degree rotation. So now we can go through and we can kind of draw all those. And our very first one is going to be just based on how we have our molecule. So based on what my eye is seeing, let's go ahead and start with carbon 2. So carbon 2 is going to be right here. And I see that carbon 1 is going to be directly down. It's going to be underneath my eye because my eyeball is going to be directly in this plane and carbon 1 is below it. So I'm going to draw carbon 1 directly below, and that is going to be CH3. And that's going to be our abbreviation for our carbon 1. So we have carbon and then we have 3 hydrogens. I then have my 2 hydrogens, and those hydrogens are wedges and dashes. And those wedges and dashes are actually coming out or in and out of the board. And based on when you're in and out of the board, but we're looking along the bond, that's kind of rotated, and that's going to be left and right. So we're going to have one that's going to be the left and one that's going to be to the right, which are going to be our hydrogens. And that's going to be our carbon 2. Our carbon 3 is going to be the back one, which we're going to draw as a bigger circle. With that, I see that my carbon 4 is going to be above my eye because it's above this carbon 2, carbon 3 bond. So going straight up, I'm going to have CH3, which is going to be associated with my carbon 4. And then I'm going to have my hydrogens, which are going to be left and right. And they're going to be facing down rather than up like my other two. And that right there is going to be a translation from my zigzag to my very first Newman projection. Once we have that Newman projection, we can then draw all of the different possibilities. So let's go ahead and choose one of those to start, and let's go ahead and redraw that one down here in our very first staggered. And actually, to make this a little bit easier, or no, we'll do full. So we'll stay in red. So we had a CH3, a CH3, and our 2 hydrogens. So that's our very first form. Now what we're going to do is we're going to take that and we're going to rotate that. So we're going to go up into this top one. We're going to take and we're going to rotate those all by. So in this case, we're going to keep our actually kind of rotated everything. But we're going to go ahead and keep one of ours the same. So let's go ahead and keep our back one the same. How about? So our back one is still going to keep our CH3 here, our hydrogen here, and our hydrogen here. And our front one is going to rotate. Because you see our front one originally was a shape like this, and now it's a shape like this. We took and we rotated that. And we're going to rotate that by exactly 60 degrees. So that rotation right here is going to take this one right here, and we're going to rotate that where that's going to be facing directly up. This one here is going to rotate where it's going to be there. And this one here is going to rotate where it's going to be like right there. So we're going to take that and we're going to spin that just a little bit. So for my groups, this hydrogen right here is now going to be up on top, which we're going to have right here. The hydrogen here is going to rotate down, and then my carbon is going to rotate over here. And I'm going to write that as H3C just because I want to show it's directly bonded to the carbon. So when carbons are on the left side, you'll write that as H3C rather than CH3. So this would now be an example of our eclipsed form, where we took that and we rotated that by 60 degrees. We can then do that again and again and again and keep rotating. So in this case, let's go ahead and rotate it another round. And in this case, my back carbon is going to stay the exact same. I'm still going to have my CH3 on top and my 2 hydrogens. That's not changing. All I'm doing is I'm just changing that front carbon And in this new rotation, my hydrogen that was on the top is going to rotate down to the right. My hydrogen at the right is going to rotate down to the bottom. And then my CH3 is now going to be on my, instead of being my lower left, is now going to be on my upper left. And that's going to be my next form. Now in this case, I have my CH3 and my CH3. They're going to be a lot closer than my last time. So this is going to be a gauche. So this right here, first one was an anti-conformation. This one right here is going to be gauche. And that's going to be one where they're 6 degrees apart. We can then go and we can kind of keep rotating this around again and again and again. In this case, I'm going to rotate it again where my ones at the top are now going to be my 2 big groups. So we'll start by just drawing my back. So there are my back 3. My carbon, which we had highlighted in yellow, is now going to be at the top in this anti-form. And then we have our 2 hydrogens. Here, this is going to be a really expensive conformation because my groups are directly on top of each other. Where here I have like a carbon hydrogen and a carbon hydrogen compared to a carbon carbon, which is going to have really, really big costs. I can go and I can kind of keep rotating this. So we're going to keep our back the exact same in all of these. And we can then rotate our front a little bit more clockwise. So we have our hydrogens and our carbon. And this is going to be another example of a gauche. You'll always go through kind of multiple gauche. And then I can rotate that one more time up to my top one. So again, keep my back the exact same. And then now I have my CH3 rotated one more clockwise, and then my hydrogen and my hydrogen. And this one is actually the same as the very first one. So I can redraw that one. And those are just both of my 100 or my 360, my 0 and 360, if you will. So these are all our kind of different possibilities. Now, if let's go and maybe get just a different color just to show our rotation of our one. So if I look at this carbon right here, this methane, or this methyl group started at like 4 o'clock. It then went to 6 o'clock, and then over to like 8 o'clock, and then over to 10 o'clock, up towards noon, over to 2 o'clock, and then back to its original 4 o'clock. Everything else kind of stayed the same in terms of the back carbon. That back carbon always had that CH3 always in the top, and we're just kind of rotating that around and showing all those different conformations. So we're able to draw those all, but now let's go and think about the actual energetic differences. So here, you're going to really have to zoom out. We're going to have a relative energy on our y-axis, and our x-axis is going to be all of our different conformations. So if we start out, let's go ahead and start out with our very first one that we have drawn. So our very first one that we have drawn that eclipsed is going to have some energy. So we're going to go ahead and just put a point that we're going to eventually connect. And it's going to be on the higher end of our curve. So we're going to kind of cut this in half. It's going to be on the higher end because it's going to be eclipsed. An eclipse is going to be a lot more energetically costly than our staggered. So it's going to be the higher end. But we know it's not going to be the worst one because we know that third one is actually going to be even more expensive because we have those 2 big groups on top of each other. Now, our first rotation is going to be 60 degrees, and it's going to get to the second one, which is going to be our kind of bottom left. And that one is going to be an anti-configuration, which is going to be the lowest energy possible, which is going to be all the way down here. We're then going to go up to our eclipsed again, and that eclipsed one is going to be the same energetics as our first one. We then can look at 180, and 180 is going to be a gauche conformation, which is going to be lower energy, so it's going to be on the lower half, but it's not going to be as low as anti. So it's going to be somewhere kind of in between here. We then go to another eclipsed, but this eclipse is going to be the most expensive because we have our two big groups. So this is going to be really, really, really high. It's going to be our highest point. And then we go to another gauche, which is going to have the same energy as this one. And then we're going to go back to our original, which is like right up here. So we're now going to go ahead and we're now going to connect all those points. So this is going to come down and then up and then down and then up, down and up, and so on like that. And that right there is going to be what our energetic landscape looks like. Now this is going to be a little bit different than our very first one. Our very first one, we had all hydrogens and we didn't have that differentiation between our anti and our gauche. We kind of had this just even, same height. Here we have something that's going to be a little bit more spread out, a little bit more complex. And each of these are going to be associated with our different type of group. So we're going to have our staggered, which are going to be on our low end, and we're going to have our anti-staggered be the lowest, our gauche staggered being a little bit higher, and then we have our two eclipsed. And of those eclipsed, we have two different energies. They don't have different names like gauche or anti, but they do have very big difference in terms of energies, where we're looking especially at like this like second one where you have big group, little group, and then our third one, big group, big group. And there's going to be an energetic cost difference or an energetic difference between those two, as well as kind of like our anti and our gauche. There's going to be some energy difference. So that curve is going to be kind of shifted up and shifted down. And here you'll see that there's going to be difference in our torsion. Some of your torsions are going to be lower and some of your rotations are going to be higher energy based on like the size of your groups. Now, this seems like a very involved problem because we're drawing a bunch of different structures and we're drawing a bunch of different kind of points. Few things to kind of take away. All of these energies here are relative. We just want to get a general idea of the relative energy between like a gauche and an anti. If you have yours that are shifted a little bit higher, a little bit lower, that's fine, as long as the anti is the absolute lowest, then you hit your gauche, which is a little higher, then you're eclipsed, and then you're like really, really big eclipsed. It's best to kind of do this in just tiny, tiny, tiny little chunks where you choose one of your conformations, and we're going to get a bunch of practice on this in class. Choose your starting conformation, and then take it and just rotate it little bit by little bit by little bit and draw all of those different ones, and then kind of identify, is this going to be my staggered gauche or my anti-gauche? Is this going to be my eclipsed? And then within my eclipsed, how are we going to compare? And as you get more and more different groups, so in this case, we had two different types of constituents. We had our methyl group, our CH3, and our hydrogen. As you continue to get more and more complex and you start adding other things, you start getting more energetic differences and starts to get even more complex. One of the main things I want you to be able to do is look at a molecule like butane and be able to draw the very first structure that we had kind of like right here, our very initial Newman projection, and then be able to rationalize at least how the different structures correspond to relative energy levels. So we'll go and stop there, and then in our synchronous time, we'll go through and get a bunch more practice on kind of working through these. But this kind of shows an idea of like a fully involved problem of thinking of a structure and then kind of understanding the entire energetic landscape that exists as we take and as we rotate one of our groups around. And that's the core principle or idea of a Newman projection. I will see you in the next one.